It's been several minutes, but here we go. The kth largest element in the stream. I think this is day 39, and I'm like, what, 3 days behind now? Buckle up. I don't know how difficult this was on LeetCode. Let me check real quick. All right, this is an easy problem according to LeetCode, asked by Amazon and Apple the last 6 months. So let's get to it. It shouldn't be too long of a video. So we have an infinite stream of integers, sorted or unsorted, called numbers. We have to find a class to find the kth largest element in that stream. So the whatever the first, second, third, kth largest element in the stream. The class should have the following functions: inputs and return values. So init, so it takes an array of integers and an integer k and initializes the class object. And it needs an add method. It takes one integer value, appends it to the stream, returns the element representing the kth largest elements in said stream. Okay, cool story. So we are looking for the 6th largest element in this array. As it is, right, the 6th largest element is 4, because we're counting from 9. 1, 2, 3. Let's make this bigger. 1, 2, 3, 4, 5, 6. So the 6th largest element is 4. If we add 40, it can't be 4 anymore. It has to be 5. The 6th largest element becomes 5, counting down from 40. So we're 40 to 9 to 8 to 7 to 6. You land at 5 when you count 6 times. 30, it shifts again and becomes 6. So that's all there is to this problem. Hope it's clear. Should be clear. And the solution is something we've seen before. Similar to 2 heap, but in this case it's just 1 heap. And it's gonna look like this. So we have k of 3, we have this stream of integers, right? So we initialize the min heap and add stream elements to it. First 3 elements to the minimum heap. And afterwards, what you want to do is check, okay, I've added these things to a minimum heap where the smallest thing is at the top. If the next element is 12, the element on top is 3, and since 12 is bigger than 3, you pop 3 off and put 12 on there, and then by default you reach the end of the list and you have the top 3 largest elements in that heap. That's all there is to it, really. That's all there is to it. And this is what that looks like in code. This is the class they asked us to implement. It has the init in JavaScript, the constructor, and an add method. It takes in k and the numbers array, the array of numbers. And in that initializer, in that constructor, we create our heap. The implementation details of a heap is not the focus of this problem. It's the use case, not an implementation detail. And then we keep track of k. We add everything in the array we call the add method on everything in the array. And while we do that, we say, okay, if k.size is less than this.k, right, just keep putting it on there, right, as long as it's before we've not hit that threshold of the numbers, the amount of the position of the elements we're looking at. Just keep adding things to the heap, which is what we did here, right? K is 3, so we don't need to check anything. Just put the first 3 things you see in the array into the heap. Then once we've crossed that threshold, we have more than 3 things. If that value we're considering is bigger than whatever is at the top of the heap, that's what peak does. Peak doesn't remove something from the top of a heap, it just tells you what the value is. If it's bigger, like in this case 12 is bigger than 3, 3 would have been on the top of the minimum heap. We kick it out, remove 3, and put 12 in there. And when we're done, we're doing everything, just peek, tell us what you saw at the top of the list, which in this case would be 6, because 6 is the smallest thing. And then we return 6. That's all. That's it. Time complexity. We're going to loop through the entire list. So we have O of n to do that. And then adding an element to the heap takes at most O of log of k time. So you multiply the two and you get n log of k. That's all there is there. Where k is the position of the element in that you're looking for. Then the add function has its own time complexity, which is O of log of k. It's that standard heap procedure. Space complexity is O of k because we're storing k elements in the heap. So space complexity is O of k. Whatever k is, it grows. Space complexity grows with the size of k. And that's all there is to this problem. Thank you for watching. See you next time.